Example 1. In this example, it showed us a capacitive displacement sensor which was designed to monitor small change in workpiece position. Okay, meaning you have a workpiece here. So if workpiece position is changed, then it will cause the sensor here to have some displacement. Alright, so the design of the sensor, we have two metal cylinder. Okay, so we can call this is outer cylinder, and the lower one here is the inner cylinder. Okay, so we have outer cylinder and another one is inner cylinder. The outer cylinder will move up and down due to the displacement of the workpiece. The distance between the two cylinders is given by D, which is the thickness of the plastic sheath or plastic bearing. So it is equal to 1 mm. Then the dielectric material in between the distance is given 2.5 here. Okay, meaning this is epsilon r equal to 2.5. Okay, the size of the cylinder given the radius is equal to 2.5 cm. Okay, so we need to find what is the capacitance value if the H here is changing from 1 to 2 cm. So let's look at this sensor. If the outer cylinder is moving up, meaning the H will decrease. If the outer cylinder is moving down, then it will cause H to increase. All right. So we need to determine what is the basic concept of this design. Okay, we have discussed, we have three ways of designing a sensor, where the first one is by changing the distance, D, by changing the area, shed area, and also by changing the epsilon, the dielectric. So which one you think this design use for designing this displacement sensor? Is it distance? Is it the distance that change? Or is it area? Or is it the dielectric material? Alright, some of you may say, oh, it is distance, because you can see here H here is basically like a displacement, so it may relate to distance, right? But it's not actually a distance, it's actually area. Alright, so because the distance between the two cylinders is fixed at 1 mm, now the shed area is changing. So the shed area is this area here. Alright, the circumference of this cylinder here. Okay, so the shed area will depend on the H, because we can calculate the shed area by 2 pi r as the length of the circumference multiplied with H. As a solution, the equation to calculate the capacitance value is C equal to epsilon naught epsilon r multiplied with area divided by D. And we do know that for this displacement sensor, the capacitance value will change due to the shed area here. So the area can be calculated based on the design of the sensor, where the area will be 2 pi r multiplied by h, because if we open the cylinder, it will be coming like this. So this is h and this is 2 pi r, the circumference of the cylinder. Okay, so now we're going to calculate the capacitance value when h equal to 1 cm. So we have epsilon naught, epsilon r, this one here. Okay, then we have 2 pi. This is r, the radius. Okay, this is radius, and this is h here. So h is 1 cm. Divide by d here, 1 mm. So putting this value into the equation, for h equal to 1 cm, we get 34.75 picofarad. Then if the h is changed to 2 cm, then we only need to change this value here. Right? All the other value are the same. Okay, so for 2 cm, it's like you multiply 2 multiply with 34.75. So you get 69.5 picofarad. Okay, so that's how we calculate capacitance value, and the value will be based on the design of the sensor. Different sensor we have different design, meaning the way of calculating the capacitance value, meaning the way of how we determine the shed area, the distance, or the epsilon, the total epsilon will be different because it's based on the design of the sensor. Second example. So this is the design for second example, where it is a variable dielectric capacitive displacement sensor. So when it said variable dielectric, meaning we understand that the distance and area is constant, but only the dielectric material will change in this sensor, right? So the design for the sensor, it consists of 2 square metal plate with the width and the length is equal, which is it is a square metal plate. So the width is 6 cm and the length is also 6 cm. Right? Then the distance, the gap is 1 mm, right? Meaning the distance is equal to 1 mm. Right. A sheet of dielectric material 1 mm thick and of the same area as the plate can be slit between them as shown in figure. Meaning there is a sheet of material that able to move in and out between the two plates. So given that the dielectric constant of air is 1, epsilon 1 is 1, and the dielectric of the material is 4. So we need to calculate the capacitance of the sensor when the input displacements equal to 0.5, 2.5, and 5 cm. So meaning when x is equal to 0.5, 2.5, and 5 cm. Right? The solution will be depend on how much the displacement of the dielectric material has been displaced. So the first one here is the total capacitance when all the material it is between the plate. And this is the initial condition. initially we consider that all the dielectric material is between the plate. Then if there is some displacement, we have to minus that displacement for epsilon 2. Epsilon 2 is our material, the dielectric material. Right? Then we must plus with new dielectric that replacing the place of epsilon 2 that has been displaced. Alright, so we multiply with epsilon naught, epsilon 1 here. Alright, and we notice that for different epsilon, it will have different area. Okay, so this is initially the area is width multiplied by length, and then it be displaced by x here. So now the area that has been displayed is width multiplied with x, and we add with new epsilon 1 here with the same area, which is width multiplied by x, this term here. So if you manipulate this equation here, the first equation here, then you eventually get the second equation here, where epsilon naught is constant, the width is constant, the distance is constant. So it will the only variable that change is the displacement x. Alright, and we have to include that epsilon 2 and epsilon 1 here. Okay, so now we have an equation that able to relate between displacement to the change of capacitance, because all other parameters here is all constant. Okay, so only x is changing. Okay, so if you replace x with 0.5 into this equation, because all the value for this one here is given. This is 8.85 picofarad per meter. The width is 6 cm. The distance is 1 mm. Okay, epsilon naught is given. Epsilon 2 is given. Length is also equal to 6 cm. Okay, epsilon 1 is given. Epsilon 2 is given. So all the values is known. Only x is changing. Right, so putting x equal to 0.5, if you calculate, you get this value, 1.2 to the power of minus 10 farad. Right, if x 2.5, then you get this value, and if x is 5.0, you will get this value. Okay, so after discussing two examples, we do know that we need to understand the design of the sensor itself, because different sensor will give you different way of calculating the capacitance value. Okay, for example 3, this is our last example. Alright, it is a level sensor. Okay, meaning we're going to measure a level of ethyl alcohol in a tank that will vary between 0 to 5 meter. Right, so we're going to use a level capacitive sensor, which is shown in the figure. Later I will show the figure. Then the following specification is given. Okay, for epsilon r for the ethyl is 26, and epsilon r for air is 1. Okay, the cylinder separation, the distance is 0.5 cm. The radius of the cylinder is 5.75 cm. L is the distance along cylinder axis. Okay, area is calculated by 2 pi RL, because this is a cylinder, so the area will be circumference multiplied with the length. right? So we need to find the capacity variation as the alcohol level varies from 0 to 5, meaning when alcohol level equal to 0, meaning all the dielectric between the plate is actually air. But when the alcohol level is equal to 5 meter at the maximum level, meaning all the dielectric material will be alcohol. There will be no air in the sensor. This is the capacitive level sensor, where we have an inner cylinder and also the outer cylinder, right? So we have inner cylinder, and this one here is the outer cylinder. Right? The distance between the two cylinders is given. D is 0.5 cm, meaning the distance is very small. And then we have R is given 5.75 cm. And we know that the level of the alcohol in the cylinder will depend on H here. H here is our level. So L is the total length, right? So we need to determine the design concept for this cylinder, for this capacitive level sensor. Alright, so we know that the area is the same, the distance is the same, it will not change. The only thing that change is the dielectric value here. So if the alcohol is at maximum level, full length, meaning the dielectric will be all alcohol. If the alcohol level is like this diagram, so it is combination of epsilon 1 plus epsilon 2. Then if the alcohol level is at 0, then it's only consists of epsilon 1. Only air is in the tank. Now we know that the only change variable is the epsilon r here. A is fixed, D is fixed, epsilon naught is fixed, only depend on the epsilon r. Either it is a combination of only epsilon 1 or epsilon 1 plus epsilon 2 or only epsilon 2. Okay, so A is fixed and can be calculated using 2 pi r per L. So L is given, R is given. Okay, then if you calculate, you get this value here, 1.806 meter per square. You have to remember that all the unit must be in meter. Alright, then the distance is 0.5 cm. Okay, 0.005 meter. Alright, so when H equal to 0, meaning there is no alcohol in there, so it only consists of air. So meaning only air will be the dielectric between the two plates. So the epsilon r for air is 1 multiplied with 8.85 picofarad per meter multiplied with area divided by distance will give you 3196 picofarad. Okay, and then if H equal to 5 cm, so meaning the tank will only consist of ethyl alcohol. There is no air in the sensor, only alcohol. So now you can see here the equation has been replaced by 26 instead of 1. Right, this is the same value as before. Then it will give you 83,096 picofarad. Okay, so this is how the level sensor, the capacitive level sensor work. So that's all for our examples. So we do know that the way of calculating capacitance value will very much depend on the design of the capacitive transducer itself. Okay, it's based on how we use the concept of capacitive transducer in order to design either it is displacement sensor, pressure sensor, level sensor, and etc. So it will affect the way of we calculating the capacitance value. Okay, that's all. Thank you.